Hello, our team is J Day and Antinvo, and in this video we will talk about the project that we reproduced for the reproducibility challenge. We have been working on a paper named AI-driven clinical decision support, enhancing disease diagnosis, exploiting patient similarity. And the main idea of the paper is very simple. Use sentence embeddings to compare new patients to past patients and guess the disease. The general problem is that the hospitals have quite a lot of patient text data, including symptoms, notes, and description. But the problem is that how can we use this text to predict a patient's disease? So therefore, the authors suggest a simple method from the paper. Number one, change each sentence into a vector or a list of numbers. Number two, compare these vectors. And number three, find the most similar past cases. And last but not least, predict the disease. The approach of the paper is quite straightforward. The authors use a biomedical model by SensVec that turns sentences into 700-dimensional vectors. Also used cosine similarity to measure how close one patient to another, and use top K prediction to choose the top 10, 20 to 60 for most of the similar diseases. And last is that to use tenfold cross-validation to test the method fairly. Therefore, our goal was to reproduce the same steps and check if we get similar results, and then move on to use the transformer-based models to compare the results with the original results from the author's paper. So from our results is that our system ran successfully, and the results were quite similar to the paper, especially when K becomes larger, recall goes up. Precision is stable. F1 scores follow the same trend, and some numbers, even though were a little low, but the overall pattern matched the original paper. And why our results are quite different. The results were a little bit low for these simple reasons. The original pre-processing part was not fully explained. The BioSenvec file that we downloaded was up to 21 gigabytes, which was much bigger than expected, especially the available storage for Georgia Tech computer only allow us to have up to 30 gigabytes. So Jay used a Mac Studio ARM, not Linux like the others, and I use the Georgia Tech Linux system, and some of the C Python code and the NLTK models needing fixing. In fact, in the original code base of the authors, some files were not included, perhaps for the purpose of experimenting. And even with these differences, the general performance was still very close. Some of the actual work we did was to make sure that everything works. Was that to fix the C Python builds on Mac operating system, install the correct sent to vector model manually, checked pre-processing step by step, and ran all 10 folds to collect the results. This helped us get stable reproduction results. And previously, we just show you the video on how to run the code to reproduce the results from the authors when using a biosent vector models. And this time, I'm going to show us how to run the code, and instead of using the biosent vector embedding models, we are going to use transformer models. There are three models that we use for testing to compare the performance with the original model that the author used. The three transformer models we use is the bioclinical BERT, the biomed BERT, and the blue BERT. So all these three models are trained from the same dataset, which is our clinical dataset MIMIC3. So this time I already have the data for bioclinical BERT and biomed BERT. This time I'm going to run the code to have it use the model blue BERT. So the blue BERT finally finished the integration completed, and we got some results right here. So what we're going to need to do is that we need to get some visualization of the data. So the first thing I'm going to do is that I'm going to git add all, git commit new data, and git push. The greatest advantage for using the transformer models is that they actually are provided by the Hugging Face, so we can streamline use the model from Hugging Face without downloading the local models like the BioSense VEC model, which is required 21 gigabytes. And I want to show you very briefly the structure of the project. Whereas what we're seeing right now is the visualization of the original outputs from the author's code that will be introduced in the paper. And now there is a visualization for the transformer model by ClinicalBird. And as we transition to the second model, which is the model from Microsoft, this is what we're seeing so far. Move to the bottom right here. There we go. Yeah. Now, I'm going to produce the visualization for our newly run model, Bluebird. And PY. One of these interesting insights is that the transformer models happen to perform quite well with the given data and with the given largest of the others. So as we can see right here is the results of the original model, whereas with the BioClinicalBird, extremely much higher, simply because even though the bars are low, I actually have to set the threshold to 1.0 because the threshold 0.6, the app score, the recording precisions all met at the value of 1. So now that's why we have a better view, a clearer insights to compare with the original code base. Thank you for your time.